Okay, so hello everyone. Thank you for joining me. My name is Aydin. I'm from Germany, and I don't know if you're familiar with it, but in Germany, everywhere we are, we take a selfie. So please cheer on three, okay? One, two, three. Yeah! Great. But I think maybe. Okay, good enough. Yeah, great. Thank you very much. I would like to talk with you about this number and what's around about this number. This is the amount of carbon emissions, global carbon emissions, our industry is accountable for. So this is the carbon emission of IT and software. And it's a huge amount. It's exploding. And to have a feeling for this number, it's twice as aviation. Yeah, it's twice as worldwide shipping. It's something similar to the steel industry. So it's a really big amount of emissions, and these are a little bit old values, so there is no AI on that. Yeah, so it's really increasing, and we have one very big advantage, contrary to the steel industry or other sectors. It is very easy for us, for the IT, to lower this value and to stop this increasing of these carbon emissions. So, and because every sector has the responsibility to care about their emissions, so the steel industry, aviation, heating, and so on, and we as the IT sector has also our responsibility, and it's a lot of easier to do that. So I prepared an agenda, some introductions into green software. What is this? What are the principles? Where are the emissions? What can I do? And what are the strategies? What tooling, data, patterns, and so on. Yeah, so first of all, are you familiar with this kind of principles of green software, hands-on? Okay, cool. And for the other, I try to give an introduction. The focus is on cloud today. But, you know, there is also a hidden agenda. And it's more about how you can smuggle in this talk today, what you see, into your daily work and business. So this is the really agenda. And the other stuff is, okay, like kind of pattern. Yep. For a better understanding, I think it's important to know where the emissions occur. Because software, there is bits and bytes, there's some text file, but the emissions, they occur on operating software or on producing software, so in the development phase, and then on the operational phase. And the emissions happened in the past because we have to build hardware to run our software on it. So we call this kind of past emissions the embodied carbon. And then we have emissions they are occurring because we are running the computers. So it's need the power and energy on that. Direct emissions. And depending on which side you are looking for, so if you are on the end user devices, then the end user devices have more on embodied carbon. So for example, this laptop has 75% embodied carbon, 80% embodied carbon. So there are 300 kilogram CO2 equivalent. and around about 50 kilograms emissions during the lifetime for 4 years. So it's based on the power. But if you look at the data center or on the server side, then it's vice versa. So there is more on operating the server because there are big machines with a lot of CPUs taking a lot of power, and so the embodied carbon is more or less 30% or so. It depends, as always in IT. And what we are doing now is understanding what happens here and how can I optimize stuff for that. For example, what to do with the embodied carbon, what to do with the direct emissions, and the direct emissions, it's not only the energy, it's more or less the fuels we burn to produce the energy. So you guys in Norway, you're fine. So we're in Germany, not so fine. So okay, and having this all in mind and thinking about that, and a lot of people have think about that, we can identify some fields of action. They're called hardware efficiency, energy efficiency, and so on. So I will go into detail into some of them, and I think you will see it, what it means, and then as an engineer, we will find solutions for that. You know, so we see the problem, and then we'll find a solution, because this is our daily job. Yeah, and what I give you today are some hints, maybe some patterns for that. Let's go deeper. So hardware efficiency and energy efficiency is about the computers, the hardware, and now we are talking more or less on server, on data centers. And in this kind of embodied carbon, so if you want to do optimization, then increasing the lifetime of a server has a huge impact. And but where is our impact? And this is, I think, very simple. As you know, so it's so what I saw and what I have done in the past is, if we have new features, new versions in our software, then usually we need more resources. So every version we have, every new release we bring out with new features, then we have more demand on that. And I think we must do the contrary. So on every new release, we must demand less resources. I think this is the job for that. So to stop this exponential increase on that. And this is really a huge impact to do that. And it depends on the software running on this. The next one, and this is, I think, the most important field we can do, is increasing the server utilization. So the server utilization means how many applications are you running on one server. So how many applications need this kind of embodied carbon. So if you increase the number of applications on one server, it means that every application needs less embodied carbon. This is most important for the server applications, and how to do that, how to deal with increasing the server utilization. And obviously do the container job. Yeah. So if you have software running on bare metal and it needs one bare metal, then it's maybe the wrong way. It's obvious. And And the third one, it's not so obvious, but it's plays in the same, it's going in the same direction, and this is this kind of, we call it idle gap. What you see is a typical load curve of a CPU, of a server, based on the CPU load. And one observation is that it doesn't start at 0. So if you turn on the computer and you have no load on this computer, so the computer does nothing, it needs energy. And this is this idle gap. And these numbers are very realistic. This is a small Dell server. So turn it on, 100 watt, bring it to the maximum CPU load, 200 watt. And this idle gap we have is always there. So increasing the server utilization means that this idle gap is split into the whole in all of these applications on this server. And the goal is to run your CPU load here. So there is a rumor at Google that if the CPU utilization is less than 98%, then the alarm is going on. So there's something wrong. Yeah? So go to the limit. And of course, the limit depends on the application and of course, how smart you are. So we have to start very fast new containers if the load comes. So be more elastic. So, but for, I think many of you have heard about this green coding and optimizing loops and data and so on. And this is true, but if your CPU utilization is here, and you do a lot of work to optimize your app to bring it here, then the saving is very less. So it's more useful to increase the server utilization. And then, if you go to the limit, then do the optimization and the optimization to get it more and better. So for faster startup and the container to be more elastic on that. Okay? So yeah, so these are the kind of principles we have to have in mind, and now we can start thinking about how to deal with them, how to increase server utilization, and the other principle of these fields of action. And I will start with the first one, with hardware efficiency, energy efficiency. That is, I bet you're all familiar with, and maybe you know more about that than I. The next step is my applications and my systems are running. We have dynamic load. We have never constant load over time in our applications. So we have dynamic load, and what is about dynamic usage of resources? So scaling. Yeah? So we will talk about that. Then we will talk something about called carbon intensity, and it's the relation between energy and emissions. So we can also play around with that. So this is the roadmap. Okay, cool. So what are the measures you can do? And I start with the trivial one. And I think the most complicated one, turn off unused resources. How many of you know or have systems on-prem, on the cloud, for tests, for acceptance tests, for dev, mirroring server systems of your customers, a lot of this kind of stuff. And there are a lot of systems, VMs and so on, and they are all running. There is data sitting in the cloud, nobody use it. And so for that, you can turn off, you can avoid it. And the problem on turning off of VMs is turn it on if you need it. So, for example, if there is, if you have different department for testing and for developing, and this big one, or it doesn't matter. So the testers or the guys who do the acceptance tests or these huge integration tests, they have their own systems and they use it. Your software, for example, for one a week or something, every week, one time or something. And they need it, but they are not allowed to turn on VMs or not in Azure. So because it's a little bit complicated with this, with the write management, so, and then it's running. So, and what we need is here some clever, smart systems, for example, that the people who want and need a VM, that they can turn it on and then work with it and then shut down. Yeah. So there is, it's not a joke. It's really the most important stuff in production. Turn off your stuff. You can also avoid something or do it without computing. So you got it. And then, of course, maximize server utilization. All you are doing is maximize server utilization. And this is mostly done by container and Kubernetes, using platform as a service, in Azure, of course, then app services, functions, use SaaS solutions instead, of having instances. And what you can have in mind is that every time you have a reservation of a resource, for example, if you have an app service environment, then you occupy embodied carbon. And if it's bigger than your reservation, then you have more occupied, you have more usage on embodied carbon. And if you are more elastic in the sense of using serverless, then you are better in this embodied carbon and the server utilization. Okay, so this is a rule of thumb for that. So, okay, done. This is secret for sustainability in software. And if you practice this, you are able to, so it depends, of course, but what I see is you can you can lower at least 40% of your emissions, at least, yeah. And sometimes you can go ahead 50, 60, 70%. So we in Karlsruhe, in Germany, we have a campaign where a local campaign where the IT companies commit themselves to reduce their emissions of the digital products for 40%, and there are low hanging. So it's really you don't have to do more than this, and if you do this, then you have also a lot of cost saving. It's cheap. Operate a cloud cheaper for less money. So there is a win-win-win-win-win situation on that, but it's more or less kind of there are a lot of reasons why something is this kind in this situation as it is. So I know that, but now we as an engineer have it in our mind that there's another reason to save these resources than saving money for the shareholder. Yeah, so it's not yet. It's not more about saving money for the boss. It's saving emission for the kids. Okay, so it's turn it. It's another way. So and it's now it's got worth. Yeah, to do that. Yeah. So and after now, so after we are finished, we can take the part 2 and go and some hints. Yeah, some patterns, maybe you know. Question? No. Okay. Start with scaling. This is a typical load curve of a system, and what I have here are compute units. So virtual compute units, take it 3 units. Doesn't matter what it is. And then over time, I get a load on my software system. And what we do, we have to provisionize our system, and the standard, I know the industry standard is if I need 3 compute units on the max, I always run 3 compute units. Do you agree? So, are you see that? Yeah. So it is a typical situation on how we run software. Yeah, it's crazy. It's crazy. And what we can do is, at least, if the load goes on, then we will scale up our resources, and if the load goes down, we scale it up. And what then happens is, you know, this one all here, this one here. Yeah? This is garbage. Unnecessary emissions. It's really garbage. Yeah? And it's useless, it has no worth, so it's only systematic. And I want to give you an analogy for if you must discuss with some guys. Once a year, I go to vacation by car. So, okay, I do it by train, but by car. And a lot of kids and luggage, so I have to buy a big car. Yeah. So I have a big car for my use case going into vacation. But in my day-by-day, I bring my kids with this big car into school, to work, and so on. So the car is oversized for my day-by-day stuff. And then, so it's useless, yeah? Too much space. And then I will park my car, because usually a car is not driving, a car is standing. And if I park my car, I will not shut down the engine. Don't shut down the engine. Yeah? So, and this is a situation on IT. So if we have it on cars, everyone would say, "Are you crazy?" So, but on the IT, it's usual. And it's more. It's really more. So currently, the situation is also, if I drive my car, behind me there is the same car driving also with me, because my first car can crash or can happen something, so I cannot drive anymore. So I can change the car and drive out, go away. Yeah? So and if I'm not driving, then I park 2 cars and with a running engine. Yeah. This is a situation in IT, and this is the case where you can really save emissions without optimizing anything. Yeah, just shut down or scale it. So, and how to scale? Where we have on Azure, there's kind of resources, virtual machines, app services, container, Kubernetes, and so on. And go read a book. Yeah, visit conferences, go to NDC. Yeah, and I bet with you that you know more how to scale Kubernetes. There are so many smart guys there. They can explain it. There are so many books on that. Yeah, and it's really easy. So on app service, you turn on scale sets. On virtual machine, you turn on scale sets. And after you have done this kind of scaling, and I'll give you some hints, then we have the situation that we can scale up and scale down, like this. But it's very hard to scale to zero, to shut down the resource. And now it's getting more software engineering. Yeah, so now we can find solutions how to go to zero, and this is the more effective. Yeah, I don't need it. Go to zero. For example, we can use functions serverless. So functions are able to scale to zero, or app service container apps can scale to zero. App services, not really. Yeah, so they have the reservation. But if you go to zero with functions and container apps, then it's gone. Yeah. So, and I want to show it. Here I have a container app, and what you see is on German, skaliert auf null, so it's scaled on zero instances. And I can start it, and now we count. So it's a container app. It's a simple app service in it. Let's count. 1, 2, 5, 6, 7, 8, 9, 10, 11, 12, 13, 16 seconds. So it's okay. It depends what is the application, but hey, on mobile and the train, it's harder. So I think it's okay. And now the application is there, so it's runnable. And depending what the application is, it could have more of this. There can have 30 seconds or 40 seconds. And if you communicate it, tell it to your customers or your shareholders that, hey, this is a cool feature. It's not a bug. It's a cool feature. We are saving emissions. Then it's it will work. And of course we can scale it up. And I will skip it for time. You will believe it. Give you an example for this. As we have produced a content management system. And this content management system runs in a container. It's a headless. And the container starts up if you want to do some data changes on it. And then it triggers a build for the web, for the front end. The front end builds and ship all the stuff into a CDN, content delivery network. And then the back end shuts down. And now I have static pages. And it's massively shared on a CDN. And I have no more the need running a web server serving non-dynamic websites. And the users, the guys who need to edit the data once a week, every 2 months, 3 times a day, I don't know, they can wait for 30 seconds. Yeah? And save a lot of emissions. Are you with me? Okay. So please tell me if I'm boring, if I'm too slow and you want to have it more faster, 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 faster. Okay, go on. This container app was a nice example, but or with the functions. But the problem is, if you have then more load on that, so you know this dynamic load here. This is a traffic app like router, yeah, where you can get from A to B and then buy some tickets and so. And they have usually, it starts in the morning. It's in Karlsruhe. It starts in the morning, then they have a peak in the midday, and then some peak in the afternoon, and then after 10, 12 o'clock, there is nothing, and after 1 o'clock, there is zero, yeah, because we have no public transportation in Karlsruhe in the night. So there are 1 or 2 persons who, in the middle of the night, must check their connection to getting to train for 1 or 2, and on this maximum, they are running a big Kubernetes cluster. So, and this is a problem. Yeah, so you cannot run your system on this serverless stuff. Because if there is load, it's very, very expensive to do it with Azure Functions or with container apps. But it's very, there are a lot of emissions in the night. So and the trick now is, or solution is, change your hosting. So in the night, I can use functions for this, poor guy has to check the connection, and on the day, if I have load, I can use, for example, the app service. And what we can do here is working with a load balancer, because the problem is that I cannot switch. It's difficult to switch the backend stuff. Yeah, you have on the night you have to go there, and on the day, so you need some kind of load balance. And I have a solution for front door. Front door is a load balancer, a DNS load balancer, kind of DNS load balancer. And the advantage is it doesn't need VNet, virtual net. So if there is not a problem, if you can use a VNet, there are more load balancer. You can also handle this with other load balancer, Scaleway or something like that. Okay, and the trick is we use a little bit of PowerShell, and then we will stop, if we want to scale down, we will stop the app service, and then we will switch our route, and then we are there, and vice versa. Okay, so this is my front door, so it's nothing magic. Yeah. You have some sources where you have some endpointers and services and so on. You configure it, and I have some. There is the Azure CLI. I can check it now. And what you see is that my web app is enabled and my function is disabled. And I have one API, is this one, with the same FQDN for the backend. And if it's going to a web app, to app service, and here is. So it's just the right one. And what I'll do now is I have to scale down. Okay, it's a little bit PowerShell magic, so you can do this in a script. So I do some copy paste, right? So I start my Azure function. Then I will switch, and I do it together. First, I update the one endpoint, so it's enabled. Then I disable the other endpoint, so it takes time to proceed that. So this is this update, and then there are 2 updates, and then a list. So it takes some time, and then it also takes some time to distribute this information into the DNS. So you have to wait for 50 minutes, 20 minutes. So it's not real time. So 50 minutes, 20 minutes, and after 20 minutes, you can shut down the other service. So this is the rule, yeah. And this is for, you can switch in the late evening and then switch in the early morning up, and then you save. With this approach, you can save the half of your emissions of your operating stuff. So, and it's a no-brainer. So there is, a little bit trick on that, but it's good. It's good enough. And we will come back later and see what happens. Yeah. And the next one, and then we go to the next patterns. This is also standard engineering. KEDA in Kubernetes. There is Kubernetes can scale. Yeah, the idea of Kubernetes is you have these pods, and the pods are running on nodes, and if there is and then you can have some kind of load manager. So if there is more load on that, then you scale up pods. And there is a built-in based on resource usage on CPU, and KEDA is based on events. So for example, if you have a queue, then based on the queue length, you can scale up more pods, or if there is more request on HTTP, you scale up. So there is an idea behind KEDA. It's standard. There are a lot of books on that, and with them you can load it. So you can scale Kubernetes in Azure with Azure Managed Kubernetes, and it's true also for AWS based on KEDA. So, and KEDA will scale the pods, and then the Kubernetes sees that there is no more resources on the node, and then they scale up nodes. And if the load goes down, then KEDA will decrease the number of pods, and then the cluster manager will also shut down nodes. Yeah? So, standard solution. Cost saving, really cost saving, very easy to handle. And the next, what you're combining with them, there are so-called vertical autoscaler. And Goldilocks is a tool which uses this vertical autoscaler and then gives you the right recommendations for your pods. Because usually, you have you do an image and this deployment, and you have some templates, and in these templates there are some limits. Yeah, so the minimum usage, so what I need on resources. And there's, for example, 2 cores, 8 gig RAM. It's a template. And you have to adjust it because maybe you need only half a core or only 1 gig of RAM. So, and if you use these kind of templates, then you waste also the resources. And Goldilocks checks it, so you run it for 1 or 2 weeks, and then you get the right recommendation for your sizing. Then you have right and proper sizing on that. So do that. Also, huge saving. Yeah. Good. But not finished. This was low-hanging, okay? Now let us change some kind of thinking, and this is the carbon intensity, the grid carbon intensity. It's the relation between electricity and emissions. You here in Norway, you have a lot of running water, so more or less the electricity power here in Norway is emission-free, but in other countries we burn a lot of fuels for that. But there is a mix on renewables and fuels. This is electricity maps. And what you see here is the carbon intensity of the different grids in Europe. We are here. Go. Or here. Or here. Oh. France, you see, they have a lot of nuclear, so it's low carbon but not renewable. So, okay, so you can think about that. Spain is good. And so if I have static computing stuff, then I can choose the right location. So be aware, not shift your computing around the world, because then you have reservation of embodied carbon everywhere. So this is an anti-pattern. And don't shift your resources to Norway if the customers are here. So you have a long range of data traveling around Europe, which costs emissions. But, and this is an example for Germany, the share, the amount of the renewables in the power in the grid, it's change over time, over the day. So basically, how many wind is there, how many solar is there? Yeah? And currently it's a good time for solar, so in Germany. Here is so more or less cold. And then I can think about it. Okay, I have some batch jobs, non-interactive load, computing load. When is the best time to execute this computing load? And this is a shift in thinking about how to use resources. Currently, we act, so if we want to have something, we get it. So if I want to have no computing resources, then it's available. But we have to change it. So what we can do is now time shifting. And for that, you need data and you need tooling. This is the basic stuff that you need. And there is a project. It's from me, and it's not my job. I'm only the maintainer. There are tools from the Green Software Foundation for this carbon-aware computing for the shifting. There is tools, and then you need the forecast data. And if you go here and want to buy the data, then you have to pay 500 euros per month per grid. This is far away from smuggling in. And this is the reason why I've done a project with these guys, Fraunhofer. There's a research institute in Germany, and we provide for open data and for free the forecast and emission data for Europe. So if you need it, want to do that, go to carbon-aware computing, and then you will find a lot of tooling. And I will now show you some of this, what we can do with it. We will react now on some signals. The first signal is how green is our electricity, and maybe do we have resources available. So, and let me show. So first, we can use container app jobs. You know container app jobs? This is this kind. You provide a Docker container into Azure, and then you can schedule it with a cron expression, for example, or manually you can run it. And the idea now is that you periodically, if you have a periodically running stuff, that you calculate the best time when you can run this job. So let us, little copy paste. Get a date, so now, and now I will ask PowerShell, and behind there is a PowerShell commandlet. I will get the next best execution time, and then let us, I can print it for you. So, and as you saw before, we are here, and it gets worse, yeah? So the best time is currently now, but you got it. So if we're here in time, and I get it here, and this graph doesn't show it, but we are forecast for the next day. So, but I want a window in 10 hours for 20 minutes. So I ask for a 20-minute job run, and it must finish in 10 hours. So, and this is the best time, and then I will adjust with some Azure PowerShell the scheduling time of my job. So it's very simple, very easy. You can do it, and sometimes it must have something better. Don't know. Okay, you believe me. Okay, you know, I prepared myself, and of course, you know, it works in the morning. Yeah. So okay, you believe me. The problem on so it's, you know, it's very lightweight, it's very easy, and you can do it. And I recommend it if you have some jobs. Do it with container apps. Do it time shifted. No brainer. if you have more complex scenarios, there is also a service in Azure. It's called Batch, Azure Batch, and Azure Batch is on VMs. So you can provide your VMs with custom setups and so on, and you can do the same. So schedule it. You create a kind of a job schedule, and then you set the limit. And the big advantage of Azure Batch is that you can configure that the Azure Batch, so the VM, should run on spot VMs. So the spot VMs are cheaper VMs, so they are you get the computing resource when it's available and good for Azure. So and they are cheaper, really cheaper. Question?
Yeah. So the script you just ran, is it for the location where the VM is placed, or is it
Where the VM or where the resources, where the grid is, where the electricity are used.
Okay.
Yeah. So currently backend.
And is there, it doesn't matter, but is there a solution for functions like a timer trigger or something?
So I don't know. There are some approaches. The question is, there is a solution also for Azure for this time trigger. I haven't found it now. There are some guys. If you can have a probe. So if you have massively done jobs, then you can start it and check, is it okay or not? And if it's okay, you run. If not, you schedule the next one. But in Azure Functions, you are also only allowed to have 5 minutes. So it's maybe, but some kind of this, yeah. But you know, we are engineers. We will find a solution. You got the principle. So. And Azure Batch is the more complex use case, but it's going. So, got it? Go to carbon-aware computing. You find the tools for a lot of stuff. There is also public API. There is a running web app, so you can ask it. It's compatible to the carbon-aware SDK. The next one, and it's getting more and more complex, is called Demandshaping. And this is the more shifting. So, you know, this time shifting, we are familiar with it. So in Germany, and so because we know it from our electrical cars. So load the car when the sun is shining, or run the dishwasher when the sun is shining. Yeah. So, and run the compute job when the sun is shining. So it's always the same principle. But now we can change it once again. And this is, we have a demand now. So we have a demand, but it's not a good time for that, to do that. So this is our, the red one is the amount of renewable. So if the red one is high, it's good, and if it's low, it's bad. And the blue one is the load. So on the left side, on the right side here, or left from you, it's okay to do the computing because the grid is green. But in the middle, it's not so good because there is, yeah. You have it. So what you have to do now is to don't do it. Yeah, don't do it. It's not good. Yeah, it's not worst. Yeah, okay, if there is something with emergency and so do it, but usually don't do it. It is a little bit hard for this interactive application. So there are some examples on that, but in general, it's hard. So if you want to do online banking, and online banking says to you, hey, guy, come on later. Yeah, in 2 hours, it's better for the planet. And then you can say, oh yeah, great, thank you for the advice. Yeah, I will come in 2 hours. Or you can say, no, guys, it doesn't belong to me. I have no kids, so I'll go on. So, it's on the interactive, but we have also this huge amount of non-interactive applications. So processing jobs, do batch, worker stuff for queues. Yeah, there are so many applications so I built which are not interactive. And for that, we can once again use Kubernetes. And we have here this carbon-aware CADA operator. And the carbon-aware CADA operator runs inside of Kubernetes. CADA is for scaling. And then CADA also, what this carbon-aware CADA operator does is he adjusts the max replica of this. I will show it. Scaled. Scaled object. This is my Kubernetes internal. And what you see is there are these max replicas here. 20 is the max replica and 1 is the min. And depending on the grid emission, the carbon-aware CADA operator will adjust this 20. So if the emission is high, so if the emission is lower than 155, then it's set to 20. If it's higher than 155, then it's set to 2. So it doesn't scale. And this is okay for all background jobs. And if the carbon emission goes get better, then it scales up. So it's a very simple trick. The only thing you need is the data. The carbon-aware CADA operator, is from Microsoft, from Azure, and it's a great tool. And they announced it on KubeConf, and I was so happy. So because this was so simple, we are looking for some interims, to do that. So it's a clever trick. It's very easy, and do that. So okay, time is running out, but I'm almost finished. So I'm pretty sure that our profession will change. The kind we are doing software will change. Currently, we do this clean code. It means we do our software right. We do this agile stuff. It means we do the right software. So, and then I think we have a new standard, and it's green coding, green. So we have also in mind that our software will be climate friendly and doesn't have a big impact on the planet. So I think this is our job, and our industry has this transition to that. Yeah, and this in mind, I have here some tags. If you want to Google it, you will find, I think, this presentation somewhere here. I'm not sure where, but you can also mail me. And please don't forget to vote. I have an advice. Take this green one. And thank you very much.